The first part of organic reactions was substitution reactions, SN1, SN2. And in this part of the chapter, we will talk about elimination reactions. Elimination and substitution reactions kind of go hand in hand, which is why most of them are covered in the same chapter. So in an elimination reaction, you have something that is leaving, all right? And so you start with a substrate and a base usually, and the end product will actually be an alkene or an alkyne, typically an alkene. Okay, so elimination, you're removing something from the substrate. When we do elimination reactions, again, there are two kinds of mechanisms for it, E1 and E2. And you probably in your mind, you're thinking about the E1 and E2 being unimolecular and bimolecular yet again, okay? And it's the same kind of thing, so we'll talk about that. The product is usually an alkene, as I said. And the other thing that is important here is that elimination reactions are called beta eliminations because the carbon that has the leaving group is called the alpha carbon, and the carbon that has the hydrogen is called the beta carbon. Now, these are not because they're alpha and beta because of the leaving group, it's because they're next to each other, okay? And so the alpha and the beta carbons, they have to be next to each other. You cannot have a carbon 2 or 3 carbons away and then have a leaving group on it, okay? And so the leaving group and the hydrogen, they have to be on adjacent carbons, and so that is called an alpha-beta elimination. We'll talk about this more also when we get into the mechanisms, okay, of the reaction. So here are a couple examples, okay, for elimination reaction. You still need the substrate, which has a leaving group on it. You need a base, and so it gives you an alkene, all right, over here. The leaving group is right here, okay, with the bromide. And then you can have a tertiary halide as well. Again, same thing, you need to have a base. And then you have elimination reaction. Now remember, we said that we have two mechanisms, E1, E2. So we will talk more about which one is favored and what kind of mechanism you. Just an overview, since you know about first order and second order reactions, this chart will be easier to follow for you now. So here we have E1 and E2 reactions. So the mechanism for E1 is first order, mechanism for E2 is second order. The rate of reaction for E1 is dependent only on the substrate, as it is in substitution reactions also. And in case of E2, it is dependent on the substrate as well as the nucleophile, just like SN2, okay? What are the conditions that you need for the substrate? For E1, you need to have, again, the carbocation that will give you a stable substrate. And for E2, you should have a primary substrate, okay? And so the conditions you can see are kind of similar to SN1, SN2. The nucleophile for E1, it is not dependent on the nucleophile because it's a unimolecular reaction, whereas in case of E2, it has to be a strong base. Please note over here, it says strong base, not nucleophile, because in case of the nucleophile, it will attack the electrophile, but we need it to be a strong base because a base will abstract a proton, okay? And so there's a little bit of a confusion here, but hopefully it will clear up as we go on. So it needs to be a strong base, okay, to cause elimination. Again, as I said before, also with substitution, there are very few nucleophiles that are true nucleophiles. That means that they do not abstract a proton, but otherwise most of the bases will act as nucleophiles, okay, and bases and nucleophiles will act as bases, bases will act as nucleophiles. So in this case, you need to have a good base. The solvent that you need for E1 is a polar solvent as usual, whereas in case of E2, in this case, you would need a non-polar solvent. Unlike what we had before, we needed a polar solvent, okay? That's the only thing that is different here. E1 will compete with SN1 and E2 will compete with SN2. And so you have to decide at one point is, what do I do? Do I do elimination or do I do substitution? Okay, and so each of these mechanisms are competing with each other, which means that you end up getting multiple products sometimes, because if you have two mechanisms going on simultaneously, then you will end up getting more than one product. Stereochemistry, we will talk more about this later on as we get into the mechanisms. In E1, it's not very stereospecific at all, whereas in E2, it is stereospecific, which means the hydrogen and the leaving group need to be in a very specific location. If they're not at orientation, then elimination will not occur. Okay, so we'll talk about this when we get into the mechanisms. But this is an overview, okay, of what is involved in E1 and E2. Let's look at the E2 mechanism first. Okay, and the E2 mechanism, bimolecular elimination, second order it means, and it requires a strong base. Okay, remember again I said base, okay, not nucleophile. Nucleophile will go for an electrophile. So it needs a good base which will pick up a proton. And also remember that a lot of bases will look like nucleophiles. Okay, so very few differences between the two. You still have to have a leaving group in there, and your product is always going to be an alkene, something that is less saturated than what you started with. You will still have the leaving group also. So here is the mechanism. Here is the alpha carbon with the leaving group on it, the beta carbon with the hydrogens. Again, if there are no hydrogens on beta carbons, there is no elimination happening. So alpha carbon with the leaving group, beta carbon with the hydrogen, and here comes the base for the proton. The proton leaves its electrons on the carbon-carbon bond, alpha beta, and then the leaving group goes away. All of this is involved in the transition state. Okay, so here again the transition state shows bond formation, bond breaking, bond formation, and bond breaking. Okay, that's what's going on in the transition state here. Square brackets with a little symbol on the top. Eventually, the base wins, it gets the proton, and the electrons are left on the carbon-carbon, and the leaving group has to go away. All right, so this is our main product over here. Bromide is the leaving group. So this is the mechanism. Again, in the transition state, you have the involvement of the base as well as the leaving group and the substrate. Okay, everything is there. The substrate and with the leaving group is still there. So since both of them are there, this is called the E2 mechanism. In the E1 mechanism, now this is a unimolecular elimination, which means first order, and only the substrate then is the rate determining step over here. The nucleophile is not as important. So the nucleophile here can also be the base. Now in SN2 and E2 reactions, the nucleophile or the base is very critical. Here in E1 and SN1, it's not so critical. And then with E1 mechanism, you also get SN1 products, which means that this is pretty much a very messy reaction, okay, to do. So if you understand mechanisms of reactions, you can actually predict what's going to happen, okay, to your reaction system. Let's look at the mechanism of the reaction. Here we start with the substrate, okay, and so just as usual with SN1, the first step is where the leaving group will go away. The leaving group goes away, so to form the carbocation, again the carbocation has to be stable, which means it has to be a tertiary halide to begin with. And so once you have the carbocation formation, now anything can happen. Okay, and anything can happen, meaning you can have substitution or you can have elimination. So if you're trying to show the mechanism for the elimination will still be alpha beta elimination. So which means that whatever nucleophile or base you have is going to abstract the proton from the beta carbon, and that will leave its electrons on the alpha beta carbon bond to give the alkene. Okay, and so the water then becomes the hydronium ion over here. So this is the product that you are predicting to have. Now, again, as I said, you can also have substitution products in here. So this really is quite a messy reaction. It will always give you a mixture. We will talk a little bit later about how to promote one or the other kind of mechanism, but in some cases you really cannot. Okay, and so you're stuck because of the kind of a substrate you have or a nucleophile you have, which means the best thing is to not do that reaction, find some other way to do it. Here are the energy diagrams for the E1 and E2 mechanism. So just like for SN2 reaction, you only have the one transition state for E2 because your base and the leaving group are all attached over here. So that's your transition state. In case of E1, you form the carbocation, and then you form the other intermediate where the base will come in. So you will have two curves, okay, over here. So the graphs here also will tell you whether your mechanism is going to be E1 or E2. Now let's look at some of the things that are really quite unique for elimination reaction. We had some unique things for SN1 and SN2 also, like inversion of configuration and all those kind of things. And in elimination also, we face the same kind of issues, okay? The issues here, of course, you don't have stereochemistry because it's a double bond, but there's another thing called the Zaitsev's rule, okay? And this has to do with the stability of an alkene. And what happens here is that there are two kinds of alkenes possible, all right? If you look at these two over here, this is what we call a terminal alkene because it is towards the end of the molecule, and this is an internal alkene because it's inside the molecule, okay? If you carefully look at this alkene over here, it is in between the two carbons which have two hydrogens and then two carbons over here. In the case of the terminal alkene, this alkene has this carbon which has two hydrogens, one hydrogen here and a carbon here, which means that this alkene, the internal alkene, had two carbons attached to it, whereas the terminal has only one carbon attached to it. Internal alkenes are considered to be more stable than terminal alkenes. We will do this a little bit more when we get to the alkenes chapter pretty soon, but this is just a little bit of a preview for this. So this is an internal alkene which is more stable than a terminal alkene. So when we look at 2-bromobutane, okay, and we start doing elimination on this, now for elimination, you need a beta proton, okay, or a beta hydrogen. And since this is a secondary carbon, there are two beta hydrogens possible, one here and one on the side. So one hydrogen can come from CH3 and one hydrogen can come from the CH2. And these are both beta carbons, so they're both valid, okay, to come out. So here, if you have a base come in and do the elimination, at one place or one of the products, you will have elimination from the internal carbon, and in the other case, the elimination will be from the methyl group, okay, or the terminal carbon. And so you end up getting two different kinds of products. In one case, you have 1-butene, in the other one, you have 2-butene. It turns out that the 2-butene, which is the more stable alkene, is going to be your major product. And this major product is called Zaitsev's product. The one that is not so popular because it's not so stable is called the Hofmann's product. Okay, we don't call it the anti-Zaitsev's or anything like that. It is Hofmann's product. So Hofmann product is not very stable and so usually will not form. Although later on we will learn about how to make the Hofmann product if you really want a terminal alkene. Just because you're getting internal does not mean that's what you want. Okay, you may actually want your alkene to be outside. And so we will learn about that. But in any case, coming back to this topic here, is if you have a secondary alkene, halide, it's possible for you to get two products, okay, in this case. So here we have a tertiary halide, and again we have the possibility of a terminal alkene as well as an internal alkene, and yet again Zaitsev's product is the more common one because this is a more stable alkene and therefore this is the major product. So whenever you have to also choose between two hydrogens, you should choose for the hydrogen that gives you the Zaitsev's product, okay, or the more stable product. So let's talk a little bit about the regioselectivity and stereoselectivity of elimination reactions. There are two very specific things. And regioselectivity, I already introduced that to you in the previous slide, which is formation of the Zaitsev's product, which is the more stable alkene, okay, the internal alkene that is more stable. So there are two mechanisms for elimination, E1, E2. So if you have an E1 type of mechanism going on, then the major product that you will get is going to be the stable alkene, all right, which is the Zaitsev's product. Once the intermediate forms, which is the carbocation, then the only way for it to go is to give you the more stable alkene. On the other hand, if you have an E2 mechanism, then you have two products possible. Okay, you have the Zaitsev's product possible and as well as the Hofmann possible. And so how do you drive one versus the other? So for example, if you have a strong base, then your major product is going to be the Zaitsev's product, all right? Because the strong base is going to go for the hydrogen. And the E2, when you have a sterically hindered base, you still have a strong base, okay, but now it's sterically hindered, whereas in the first case where we got the Zaitsev's product, it was not a huge bulky base. But in the second case where we have a huge base, then that huge base is going to go for a hydrogen that is easily accessible, which is towards the outside, okay, which means towards the terminal carbon, and therefore the alkene that you will end up getting is the Hofmann product, because the alkene will be then terminal alkene, okay, or towards the less substituted carbons. So in a way, with these two pieces of information, you can actually drive your reaction and see if and try to get one kind, okay, whether you get the Zaitsev's product or the Hofmann product. So it's a little bit more control over your reaction. The other part of selectivity in E1, E2 is stereoselectivity. Okay, and stereoselectivity is important because this is according to the orientation that you have for the leaving group. Okay, and so remember, in elimination, you are removing the beta proton. So the beta hydrogen and the leaving group, they have to be in a very certain orientation in order for them to actually leave, all right? And the orientation is actually opposite to each other, which means that the dihedral angle between them should be 180, which means they should be anti to each other. So if they're not anti to each other, then it's not a very good orientation and elimination does not occur. However, if they are in complete opposites to each other, like an anti-orientation, then elimination is very easy. Okay, and that is called stereoselectivity. Also because the molecule is kind of stuck in a particular orientation. And this orientation we learned about back in alkanes when we talked about conformation. So each molecule has its own conformation, and sometimes the conformation will support this anti-periplanar geometry. In some cases, the conformation does not support it, and if it doesn't, then elimination cannot take place. All right, so this kind of an opposite thing is necessary for elimination to happen, and that is called stereoselectivity. So here is an example, okay, for the cyclohexane. First of all, the equatorial groups are never going to be in the proper alignment for elimination because they're not sticking out there. They're at an angle, so they're not quite accessible. So which means that the hydrogens that actually have to leave will be axials, okay? And so if you have your leaving group over here, the two hydrogens that are available for elimination are going to be anti to it, okay, which means that they're trans according to chlorine. If chlorine is going down, hydrogen should be going up, and also axial. All right, so chlorine here is axial going down, hydrogen has to be axial going up, and the other beta hydrogen also axial going up. All right, and so then you get the elimination reaction here. In this case, where chlorine and hydrogen are in equatorial position, then there is no reaction because the conformation is not good. So the dihedral angle here has to be 180 for the reaction to take place, okay, and it can't be a small angle. So even if you have chlorine and hydrogen, one equatorial, one axial, even then it's not happening. Both of them have to be axials, and that's when you get the reaction. And that is called stereoselectivity. So here's a problem that I would like you to work on your own. Okay, I'm giving you the products and I'm giving you the starting material. So you know what's going on, you just have to explain it. Okay, so what you're going to do is you're going to look at these two stereoisomers that we have, the cis and the trans. And here you have the two groups, the chlorine, which is the leaving group, and an isopropyl group next to it, which are cis to each other. And then in this case, in the bottom case, you have trans to each other. Okay, so the leaving group and the isopropyl group are trans. So when you have a cis relationship and an elimination reaction happens, you end up getting two products. This one over here, the first one is the major product, and this is the more substituted alkene. This is the Zaitsev's product. This one over here, the second one, is not the Zaitsev's product. This is the Hoffman product, and this is the minor product. So then you have to tell me why this happens, okay? In case of the trans, okay, you only get the minor product. So your minor product really is your major product. You don't even get the other one. So which means that in case of the trans relationship of these two groups, you do not even get the Zaitsev's product, all right? Which means that synthetically speaking, you are kind of the winner because you know exactly what you're doing now and what kind of product to expect. But the thing is that I need an explanation for this. Okay, so I need you to work on your own on this one. Write the conformers that you will have for cis and trans, and then see what kind of relationship is between the chlorine and the hydrogen. Remember, the chlorine is over here, so this is alpha carbon. The next to it for the isopropyl, this one and this one down here, these are the beta carbons. So you need to figure out the protons and these two and then see how the elimination works. Okay, and so you cannot do this without drawing the chair conformations. So the biggest question that arises after we learn about elimination reaction is, what do I do? Do I do substitution or do I do elimination? What do I do? So it's a little bit um, of a problem sometimes, but we can clarify a little bit. Okay, so for example, in case of substitution, your nucleophile has to have a good strength. Okay, so if you have a good nucleophile, then you end up getting SN2 reaction. Remember, it has to be a weak base. If it is a good base, then it will abstract a proton, and then it will not give you substitution. It will actually give you elimination, all right, which is what you need over here then. So for elimination, you need a good base, all right, but for substitution, you need a strong nucleophile. The nucleophile size for a substitution reaction should be small. Okay, so it's able to access the electrophile, which is the carbon, okay, which has the leaving group. In case of elimination, it's not really important for that nucleophile to reach the carbon because that's not what its goal is. All right, so for the nucleophile to do elimination, it needs to access the proton, which is usually on the periphery. Okay, and so your base here or your nucleophile can be bulky. The substrate. The substrate for substitution needs to be primary substrate, and it gives you a fantastic SN2 reaction, not SN1, because a primary substrate will give you only SN2. So you end up getting SN2 reaction, okay, or a substitution if your substrate is primary. But if you have a tertiary substrate, then you're in trouble, okay, which means that you end up getting all different kinds of products. Now, E1 and E2 will give you the same kind of product, which means you'll get an alkene, but the mechanism that is followed is both for E1 and E2, and then you also get SN1. So there is substitution products and elimination products is pretty much a mess. Again, if you see over here, we are missing the secondary substrate. And again, we're missing the secondary because secondary can go either way depending on the nucleophile and such. The last thing is temperature to talk about here. And higher temperature will promote elimination. So if you want to promote elimination versus substitution, okay, especially when you have, equal kind of nucleophile with the base strength, then you need to have a higher temperature, and that will give you a little bit more elimination than substitution reactions. Okay, all right, a little bit more specific about E2 versus SN2. So substitution versus elimination, second order. All right, so for second order, you need to have a tertiary halide that will give you more of an E2. All right, remember, for SN2 reaction, you need to have a primary halide. Okay, but if you want to get an E2, then you're better off with a tertiary halide and a bulky base. Okay, because then your electrophile is not easy to access. And if the electrophile is not easy to access for the nucleophile, then it will go for the proton. All right, so you need to have a tertiary halide and a bulky base, gives you E2. As far as E1 and SN1 is concerned, really there is not much you can do except for temperature. Okay, otherwise it's really kind of a mixed bag. So you end up getting a lot of products in this case. So heat is the only thing that will help you a little bit more with the elimination. Okay, now a little bit about the alkyl halides. Okay, so if you have a primary halide, you can almost always expect SN2 unless you have a strong base. Don't forget that. If you have a strong base, then you will end up getting E1 also, E2 also. Okay, but usually with primary halides, you will end up getting SN2 reaction. With secondary halides, okay, with secondary halides, you will end up getting SN2 reactions most of the time, except when there is a bulky base. What is a bulky base? A bulky base is like T-butoxides. Okay, methoxides are small bases. Hydroxide is a small base. T-butoxide is a big base, and some of the other bulky ones would be just larger in size. Okay. For tertiary halides, really you cannot do much. As you can see, it's still a mess. You will get all sorts of reactions going on. Sometimes if you have a strong base and high temperature, then you can promote elimination. Okay, and if you have a tertiary halide, then you're promoting a little bit more of E1, okay, type of a reaction. So here are a couple examples to look at, okay, to see whether we have substitution or elimination going on. So in the first reaction, okay, we have a primary halide and a nice small base. It's not that small, but it's not that big either. It's a nice strong base. And so with this, your primary product should be an SN2 product, okay, without any issues. If you have a secondary substrate, the same kind of a nucleophile or base, but you have now a secondary halide. In case of a secondary halide, now you're promoting more of E2 because in this case, this carbon now is not so accessible to this little bit of a bigger nucleophile, and so it would prefer to go to the hydrogen. Okay, so it will pick up the beta hydrogen, and your primary product then will be elimination reaction. The kind of questions that you get for substitution and elimination is, of course, predicting the product. Most of the time, you will be asked, what is the major product? So which means you don't have to give both of the products. You have to figure out which will be the major product. Okay, so you don't have to give both all the time. In fact, you should not give both of them. So your concepts for this portion are also the same kind, that you need to know the transition states and nucleophile, electrophiles, leaving groups, carbocations, all those wonderful things. So it's the same thing as substitution reactions. It's nothing much different. The mechanisms are the same, transition state diagrams are the same. The only thing is that you're producing alkenes instead of substitution reactions.